Welcome to the second lecture on Markov chains. In this lesson, I'm going to go into more detail on some concepts that I introduced in the previous lesson, but want to get a little bit more technical here. And the particular topics are irreducibility, classification of states, and periodicity. I introduced the concept of irreducibility a couple of times in the previous lessons from this playlist, and I want to tie the definitions together here. In terms of Markov chains, we said a Markov chain is irreducible if it has one communication class. In other words, you can get from one state to any other state in a finite number of steps. And then in the lesson on non-negative matrices, I defined an irreducible matrix as a square matrix that cannot be permuted into block upper triangular form by any permutation of its rows and columns. This property ensures that the matrix cannot be decomposed into smaller independent submatrices. So if you can decompose a matrix into submatrices, then what you end up having are states that can communicate amongst themselves within a smaller communication class, but they can't communicate to states or transition into states that are in other communication classes. In other words, you have a reducible Markov chain in that case. So the point of this is that an irreducible Markov chain is one whose transition matrix is irreducible. So that ties these two things together, at least in terms of Markov chains. Then I want to continue with the idea of irreducible. Let's take a set of random variables x sub n that defines a Markov chain with transition matrix T, and let bold face 1 be a column vector, and then it has a 1 in each position, 1 being scalar now, it's not bold. Since the rows of a transition matrix of a Markov chain always add to 1, we have this equation here. But we can see that implies that 1 is an eigenvalue of T, and then the column vector 1 in bold is the corresponding eigenvector. From the lesson on non-negative matrices, we had theorem 82, which said that the Perron eigenvalue was between the maximum row sum and the minimum row sum. But for a transition matrix, the row sums always equal 1. That means the Perron eigenvalue R, which we called in that lesson, is 1. And we can take the column vector 1 to be the corresponding right eigenvector. The Perron-Frobenius theorem says there's also a positive left eigenvector V, which we can normalize so that its components add up to 1. And it satisfies that this is basically the equation for a left eigenvector. So we have this, and I could have put I guess I should have put a 1 there, a scalar 1 times V. And so that's the consequence of having a Markov chain. Then the related concept is this idea of a stationary probability. If you have a probability, which we can make the initial probability of a Markov chain, and it has this property here that the initial probability equals the probability after 1, 2, 3, 4 n steps, then we say that the probability distribution is stationary, and that's equivalent to this, which you notice is the same as this, what we have here. A Markov chain with such an initial distribution is said to be stationary. So I'll show you an example of this on the next slide. So I have an example here of a stationary probability for a matrix, transition matrix representing a Markov chain. So here's our transition matrix. We can do a quick check. You can see each row adds to 1. And then I'm not showing you the calculations, but this row vector here satisfies this equation. So this is actually a stationary solution to this here. And I checked it out myself. I multiplied this times the first column, and then the second column, and the third column, and you get back the same vector. So here's one example. Now let's look at the conditions under which we have a solution. We have a stationary vector, stationary probability. On this slide, I summarize the conditions under which a Markov chain has a stationary distribution. If the state space is finite, and that's kind of what we've been looking at mostly, and the Markov chain is irreducible, every state can eventually reach, in other words, every state can eventually transition to every other state, and aperiodic, no fixed cycle structure, then under these conditions, a unique stationary distribution exists, and the chain converges to it regardless of the initial distribution. What converge means that when you take powers of the transition matrix, the rows eventually converge to this initial distribution, this stationary distribution. And we'll get more into some of the details later. If it is irreducible but periodic, then it referring to the Markov chain, then a stationary distribution still exists since it is finite and irreducible, but the chain doesn't necessarily converge to it. So oscillation persists. And then if the Markov chain is reducible, at least one stationary distribution exists, supported on the recurrent states, but it may not be unique. We'll get into periodic and aperiodic later, but I just thought I'd at least give you a definition up front here, just to kind of give you the full picture. So formally, for a state I, let this thing here, this expression be the set of times at which the chain can return to state I. So it would be some discrete number, 1, 2, 3, 4, whatever. The period of the state I is defined as the GCD of all these possible times at which you could return back to the state, the given state. If the GCD is 1, the state is classified as being aperiodic. If all the states in a Markov chain have a period 1, then the entire Markov chain is classified as being aperiodic. I have a theorem on this slide related to some of the concepts we've been talking about in the previous slide. A finite irreducible Markov chain has a unique stationary distribution given by the solution V to the equation V times the transition matrix for the Markov chain equals V, where the V times the column vector 1 equals 1. And let's take a look at the proof. In the previous lesson, we derived this formula here. These were Pn and Pn minus 1 were row vectors, and T is the transition matrix for a Markov chain. And that was part of the Chapman-Kolmogorov equations. If we let V equal our initial probability distribution, where V is the left eigenvector of the Perron eigenvalue, which we know to exist from the Perron-Frobenius theorem, then we have this first line here. This first equality comes from this. Then this going from here to here is from this equation. And then because V is the left eigenvector, we have this here. And then we plug back in and we get P0. So P1 equals P0, and you can go through the similar calculations and show P2 equals P0, and in general, Pn equals P0. So in other words, if we let the initial probability distribution equal the left eigenvector corresponding to the Perron eigenvalue, then we've shown it's a stationary distribution, and in fact the Markov chain is classified as being stationary. Conversely, if P0 is a stationary distribution, then we have these properties. This is by definition. Probability distributions, of course, are greater than or equal to 0, and then we know that the sum of the probability distribution is 1. But by the uniqueness of the Perron-Frobenius left eigenvector of T, that means that given these conditions here, that P superscript 0 must equal V, the left eigenvector corresponding to the eigenvalue 1, the Perron eigenvalue. I just want to remind you of a definition before we get into this slide. This was from my first lesson in this playlist concerning a primitive matrix. And a square non-negative matrix A is said to be primitive if there exists a positive integer n such that a to the n is greater than 0. So we're going to need this condition in the theorem that we talk about here. So let me introduce the theorem. The following theorem is important in Markov chain theory since it states for a primitive Markov chain, the probability distribution x sub k approaches v as k approaches infinity, i.e. the limit as k approaches infinity of the transition matrix to the k power equals the column vector 1 times v, where v is the left eigenvector corresponding to the Perron eigenvalue. We've talked about that in the last slide. This result is independent of where you start. So no matter what your initial probability distribution is in this case, you'll eventually hit this limit here, 1 times v. Further, and I read this somewhere, and I'm not completely convinced this is 100% true, but the claim is the rate of convergence is very fast, and thus it goes, where I read this, it says, thus, after a few transitions, past history becomes irrelevant. So I'll explain in an example what maybe someone meant by saying this, but I don't think it's very fast, but you'll see what I mean. So here's the theorem. For a primitive Markov chain, notice primitive, and that primitive is referring to the transition matrix, with unique stationary distribution V, and that's the left eigenvector corresponding to the Perron eigenvalue, and transition matrix T, the limit as k approaches infinity of t to the k equals 1, column vector 1 times v. That this is in fact a matrix, and each row of the matrix is v. So what it's saying is that if you raise t to a high enough power, all the rows are going to look the same, and they're going to look like the stationary distribution v. And I referenced this book before in my previous lesson, but I can give you the link again by sending it if you're interested in the proof of this. Okay, so let's look at an example, and I'll give you a better feel for what's being mentioned here. Actually, I have two examples. The second example is the one where I'll talk about the not so fast convergence, at least in my opinion. Consider this first example is more just finding the stationary distribution. So we have an irreducible Markov chain, state space 0, 1, 2, so on. And these are the transitions. So from 0, and go back to 0 is 2/3 probability, and from 0 to state 1, you can go with 1/3 probability, and then this is the transitions out of state 1, state 2. And if you draw this, you'll see that you can go in between any of the states, eventually going out further and further. So this is irreducible. In order to find the stationary probability distribution, we need to solve this equation here. So we multiply v times the first column of t, and we get this. Then we can go down to v times the ith column of t, and we get this here. So this is for I greater than or equal to 1. You notice you always have 1/3, 2/3, 1/3, 2/3. There would be another 2/3 down here. So you have this equation. And then this is enough to find our v. We first solve this first equation in terms of v1 in terms of v0. Then we plug 1 into this. We get this here. And we put v1 in here, and then we get this in terms of v0, this in terms of v0, so we can solve for v2 in terms of v0. We get this, and then we put 2 in here. We get this equation, and we plug in v2 here, v1 here. So these are both now in terms of v0, and we can solve for v3 in terms of v sub 0. We get this, and then the pattern continues. So vn equals 1/2 to the n power times v0, and then it tells us our stationary probability distribution equals this, but we want it to be a probability distribution. So if we add these up in here, this is the geometric series, it adds to 2, and so we need to make v0 1/2, and then this will add up to just 1, which is what we want. And then we put in v0 equals 1/2, you get 1/2 to the n plus 1 for v sub n. Okay, so that's generally how you go about finding a stationary probability distribution. You need to solve some equations, you look for a pattern, and then you need to make sure what you find actually is a probability distribution. So you normally would need to set this parameter here to something to counteract what this sums up to. In our case, it was 1/2. Our second example is a version of the previous example. It's even simpler. We just have 4 states, and we adjust the transition matrix as shown here. So you still add up to 1 for each row, but here on this last row, you can't go any further out. You have to come back. So you're going from state 3 back, either going back into state 3 or back to state 2. So if we solve this equation as we did before and then normalize v, we get 1/2, 1/4, 1/8, 1/8. And here's what bothered me about the claim of being fast convergence. If you raise this to the 4th power, you notice you're still pretty far off. You're expecting that each one of these rows is going to be close to these numbers here, and you're pretty far off. You go to the 8th power of t, which is this, and I mean here this should be 1/2, and it's not even close. These should be 1/8, so you're still kind of pretty far off. 32, excuse me, if you raise this to the 16th power t, raise this to 16th power, you get this, or this is getting somewhat close. And when you get to 32, then you're starting to get accurate to about 3 decimal places. So for me, that's not really fast. Maybe this is a bad example. Maybe what someone meant is that if you square this and then raise it to the 4th power, and then you can square this again and you get to the 8th, right? And if you square this again, you get t to the 16th. So you're really like only doing 5 squarings to get to a very accurate solution. So maybe that's what's meant by fast, where you take advantage of squaring and then squaring again and then squaring again and getting the so there's no reason to do 5, 6, 7. You can just keep squaring. If your only goal is to figure out what this converges to, you can just keep squaring the transition matrix over and over, and then, as I say, by the 5th squaring, you're pretty close. Recall the 2 states, I and j, of a Markov chain are said to communicate if they are reachable from one another by a sequence of transitions with positive probability. This is equivalent to the condition, the probability of going from I to j in n steps is strictly greater than 0 for some integer greater than or equal to 1. A Markov chain can be divided into a collection of states that communicate amongst themselves. In other words, they can transition amongst themselves. And we can state this more formally in this theorem. A Markov chain with a finite or countably infinite number of states can be uniquely decomposed into a collection of disjoint subchains, C1, C2, etc., whose union is the entire Markov chain such that all states within a subchain communicate with each other but with no other states. Then we have a term here we mentioned earlier. Each subchain is known as a communication class. A Markov chain with only one communication class, in other words, where all the states can transition to one another in a certain number of steps, is referred to as an irreducible Markov chain. Then I have a couple of examples. The gambler's room, which I don't believe I mentioned before, but I can give you a quick overview of that. So you have, for example, 2 people gambling on some card game, and between the 2 of them they have $8, and this is the states for one of the 2 people. So If one of the gamblers loses all their money and they're in zero state, then the game stops. So this is an absorbing state. Then that one person could oscillate between having won and A minus $1. But if the that particular gamble gets up to $8, that means the other person just lost all his or her money. And again, this is another absorbing state. So you have three communication classes: 0, then from 1 to A minus 1, and then just A, the total number of dollars being owned by one of the players. For the unbounded one-dimensional random walk, which we saw earlier, there is but one communication class, and so the Markov chain again is irreducible. And I have another example of some communication states in the next slide. On this slide I have a transition diagram for a Markov chain, and I claim there are three communication classes. Let's have a look at them. 0, 1, 2. Notice you can go from 1 to 0 to 2 to 1 and back, so you can communicate amongst these. Let me circle them, and you can't get out of these three. You notice from let me point here. You're going from you can go from 3 to 2, but you can't go the other direction. So this is sort of one communication class. And then you have the one in the middle, 3. You notice you can. The only way you get into 3 is if you initially start there, and then the next transition you're going to leave for sure. And then you have something similar on the right. You can go from 5 to 4 to 6 to 5, and you can also oscillate between 6 and 4, but you can't get back out. So this is another communication class. Okay, so this is Markov chain with 3 communication classes. In addition to the probability of a Markov chain returning to a given state, we're also interested in the number of steps it takes to return. And to that end, we define this quantity here, tau II, and that's the minimum for an integer n greater than or equal to 1, such that x sub n, this is the random variable representing the Markov chain, equals I, given that you started in state I. So the minimum number of steps getting back to where you started from for a given state. If no such n exists, the Markov chain never returns to state I, and then we say that this quantity tau II equals infinity. So our state number 3 in the middle of the diagram from the example in the last slide, that would have this property here, because once you leave, you never come back. There's no minimum number of steps. It's basically infinite. You don't come back. Excuse me. So further, we define f sub II as the probability of ever returning to a state I, given that you started in state I. And then we have these more precise definitions of recurrent and transient, which I've mentioned before, but this is a more accurate definition. A state I is defined to be recurrent if FII equals 1. So in other words, you have a probability of 1 of coming back to that state. And transient if FII is less than 1. Notice it's not 0, it's just less than 1. And some sources, some books, papers, they use the term persistent rather than recurrent. And then we have a little bit more here. By the Markov property, which I've copied, this is from our previous lesson, the first lesson on Markov chains. Each time a Markov chain visits a state I, it will return with the same probability, FII, that's because of the memoryless property. So if FII equals 1, state I will be visited an infinite number of times, thus the term recurrent. And if FII is less than 1, state I will only be visited a finite number of times. The total number of visits to state I, starting from state I, is given by this equation, capital N sub II, the sum from n equals 0 to infinity. It's just counting the number of times you start from state I and then you return to state I. This is an indicator function, so it just counts the number of returns. We can define the indicator function here in general, and the indicator function I of some event A equals 1 if A occurs and 0 if A does not occur. So the probability that the indicator function equals 1 is the same as the probability that A occurs, and the probability that the indicator function equals 0 is the probability A does not occur. That's what this little symbol means here, not A. Further, the expected value of the indicator function of A is 1. In other words, the value 1 when A occurs, and then 0 when A does not occur, and then you add it and you just get probability of A. So there's a 1-to-1 correspondence between the expected value of the indicator function of an event and the probability of that event. The random variable n sub I, which we've defined up here, has a geometric distribution when Fii is less than 1. In other words, when I is transient. It's given by this equation here. The interpretation is that you return back to I n minus 1 times this probability, and then you never return after that, 1 minus Fii. So it's a total number of n visits. You start in I, and then you come back n minus 1 times, and then you never return again. So that's a transient state. Based on our ideas from the previous slide, we have a few more equivalent definitions of recurrent and transient. The expected number of visits to state I, this quantity here, is 1 over 1 minus Fii. This is just the known result for the expected value of a geometric distribution. This gives us some additional equivalent definitions for recurrent and transient. So a state I is recurrent, in other words, Fii equals 1, if and only if the expected value of NII is infinite, and the state is transient, Fii is less than 1, if and only if the expected value of NII is equal to the 1 over 1 minus Fii less than infinity. And I should point out it's also possible for this to be 0. Fii could be 0. I kind of maybe suggested that wasn't the case. It doesn't have to be 0, but it can be 0, and that means that you have a state where you have, the only possibility you have is to leave it, as we saw in the example a couple of slides back, state number 3. So that's a possibility. Using the indicator function, which I described in the previous slide, we have the expected value of NII is this here, just plugging in what NII is, and then that we know from the nature of the indicator functions equals this probability, and so that's just the sum of the probabilities of returning to I in 1 step, 2 step, 3 steps, and so forth. And so if this sum is infinite, just matching it up with this here, then the state is recurrent, otherwise the state I is transient. We have the following theorem. If state I is recurrent and state I communicates with state J, in other words, they're in the same communications class, then state J is also recurrent. And you have the same thing for transient. If I is transient and I and J are in the same communications class, then J is also transient. So we have two cases. Take the case where I is recurrent. Since I communicates with J, we know that there's integers k and m such that we can get from transition from I to J in k steps, probability greater than 0, and we can get back from J to I in m steps with probability greater than 0. Thus, for any positive integer n, we have this inequality here. The expression on the left allows for any root between j and j in m plus n plus k steps. There's no restriction here. So this has a higher probability than this right side because the quantity on the right is the probability of returning to j in m plus n plus k steps, but the added restriction is you need to go from j to I in m steps and then return back to I in n steps and then go from I to to j and k steps. So this has restrictions on it, and so this probability is bigger than this. And if we sum over n, we sum this over n, then this is greater than this side here. These two terms don't involve an n, and we know from the definition of recurrent, this here is infinite. And so this probability is, well, it's greater than or equal to infinity. It equals infinity in that case. And so that implies that j is also recurrent. Then the other case is simple because we've already proven the hard part. This follows easily from the above result, for if j were recurrent, then we know I would also be recurrent. So the only other possibility is j is transient. We have a couple of theorems here. I pretty much said this one already, but I'll just read it off. Theorem 89 follows from what we just proved. If I and j are in the same communications class, then both are either recurrent or transient. Remember, transient and recurrent are opposites, so if you're not one, you're the other. Further, for an irreducible Markov chain, either all states are recurrent or all states are transient. That's true because you only have one communication class in an irreducible Markov chain. And then we have this theorem here. An irreducible Markov chain with a finite state space is recurrent. And I have a proof of that. If a Markov chain has a finite state space, then not all the states can be transient. Otherwise, after a finite number of steps, the chain would leave every state never to return and thus go nowhere. So that means there's at least one recurrent state, in which case, if it's an irreducible Markov chain, the whole chain is recurrent. I've mentioned periodicity a few times, and I wanted to give the exact definition here on this slide. The states of a Markov chain can be periodic in terms of return visits. For example, the states in a one-dimensional random walk are all of period 2, since the return time in steps is always an even number. And this is the exact definition. The period of a state x is the GCD of all the possible return times in n steps, where the probability, of course, is greater than 0. So if you had a state in a Markov chain where you could return in exactly 3 steps or exactly 5 steps, and those were the only two possibilities, then the GCD would be 1 in that case. For a given state, if the period is greater than 1, then we say the state is periodic. For example, if, and this is not periodic, but for example, if for a state x in a Markov chain, we have the probability of returning to state x, starting from state x in 1 step, then the state x is aperiodic, since the GCD would be 1 in that case. Then I have an example here of a 4 states that are periodic. Let's look at each one. So you can go from 1 to 2. The only choice is to go to 4 and then back to 1. So this is 3. The period is 3 for 1. And of course, you can return back in 6 steps or 9 steps. You can keep cycling, but it's all multiples of 3. So the GCD of that would be 3. And the other 3 states are the same way. Let's look at a few more. So from 2, the only choice is to go to 4, then 3, then back to 2. So you can come back in 3 steps or 6 or 9. So the same deal was 2. Let's look at one more. Let's look at 4. So from 4, we can go to 1, to 2, and then back to 4. Or we can do it in 6 steps or 9. So again, the GCD of the different possible return times is 3. So we have and the same thing for 3, which I didn't go over. So each of the states in this Markov chain are periodic, and they're of period 3. Periodicity, like recurrence and transience, is a class property that is shared by all states in a communications class. We have this theorem here. If states x and y are in the same communications class, then their periods are equal. So for proof, since x and y can communicate, we know there exist positive integers k and m, such the probability of getting from x to y in k steps is greater than 0, and from going back from y to x in m steps is greater than 0. Then that gives us this here. It's just saying the probability of returning back to x in k plus m steps is greater than or equal to the probability of going from x to y in k steps and then from y back to x in m steps. And the reason for this is an argument we've been using a few times, but I'll mention it again. This is true since the paths from x to x of length x plus k plus m, include, in other words, are a superset of the set of paths from x to x going first from x to y in k steps and then from y to x in m steps. Since x has period dx, k plus m must be a multiple of dx. So we have this as one fact. Next, let L be any positive integer such that the probability of starting from y and returning to y in L steps is greater than 0. And we know that such an L exists because we can go from y to x and then x back to y. Basically, this argument here was using y instead of x. Using a path argument similar to what we had in Theorem 88 as well as here, we have this. So going from x back to x in k plus L plus m steps has more flexibility, more possibilities than this more restricted path. It's still going from x back to x in k plus L plus m steps, but you have to enter y in k steps, return back to y in L steps, and then go from y to x in m steps. So since x has period dx, k plus L plus m must be a multiple of dx. So we've now shown two different things are a multiple of dx, and so their difference must be, and the difference of this and this is L. Thus L must be a multiple of dx. And since L is any positive integer, where this is true, it must be that dx is the divisor of all such L. And so dx is less than the period of x is less than or equal to the period of y. That's by the definition of the greatest common divisor. And then we can just reverse the roles of x and y and go through the same argument, and then we'll have the period of y is less than or equal to the period of x, and of course that implies the period of x and y are the same. So let's finish this lesson with a couple of examples. The Markov chain in the figure down here is irreducible. Every state can be reached by every other state. I'll let you check that, although we can do a few here. You can go from 1 to 2 to 3 to 5 to 6 to 7 to 8. I guess that's maybe the two that are furthest apart, just to give you one example. So by Theorem 91, we only need to determine the periodicity of one state to determine the periodicity of all the states. Let's analyze state 4. You may want to try a different one, but I'm going to do state 4 here. So we have the following paths in returning to state 4. We start here, we can go 1, 2, 4, so that's 3. And then we have 4, 3, 5, 6, 7, 8, 3, 2, 4. That's 8 steps. There are other return loops, but there are all combinations of these loops here. The GCD, greatest common divisor of 3 and 8, is 1. Therefore, the period of 4 is 1. Thus, state 4 is aperiodic, and by Theorem 91, all the states of the Markov chain are aperiodic. And I have one more example where I modified this a little bit. The irreducible Markov chain in the figure below is a variation of the Markov chain from the previous diagram with one additional state. With this modification, The Markov chain is now periodic. If we consider state 1 and analyze that, we can see that the period is 3. So from state 1, you can go 1, 2, 4, 1, that's 3 steps. You can go 1, 2, 4, 3, 2, 4, 1. That's 6. And of course, you can cycle multiple times through these, and you're still going to get a multiple of 3. And then the more difficult one is where you go out here. So you go from 1 to 2 to 4, 3, then 5, 6, 7, 8, 9, back to 3, 2, 4, and then 1. That's 12 steps. Okay, so all the other cycles back to 1 are multiples of some combination of doing these multiple times. So the period of 1 is 3, and thus by our theorem 91, all the states of the Markov chain are a period 3. Okay, so that's the end of this lesson. Maybe just a little antidote here. I tried to get some of the AI programs to check to see if I had made a mistake, and I tried with Grok and DeepSeek, and they had trouble interpreting this diagram. I gave it the diagram. So I actually put this into a matrix format. So this is showing the transitions here. And then I gave it to ChatGPT, and it went through the analysis, and it did get 3. So that makes me feel good that I didn't miss anything on this. Okay, so I have one more lesson in this entire collection of several playlists for my book, and that's on least squares. And once I get that done, I'm going to do some work and get my book and publish it on Amazon. And I'll let everyone know about that.